So we'll continue with this linear algebra numerical analysis. Oh, this is the title there. So we have the numerical analysis portion now. And in numerical analysis, we will continue with the iterative methods for solving system of linear equations. So we are familiar with already system of linear equations in linear algebra. So this is very much in continuation to linear algebra. In fact, sometimes we teach in linear algebra also. So it is a topic which is common in both. It comes under computational linear algebra category there in linear algebra. Otherwise, it can be also taught in numerical analysis. So mainly we'll look for the iterative methods for solving system of linear equations. And there are two methods which you will be covering in this lecture. One is the Jacobi method. The other one is Gauss-Seidel method. So these two methods we will be discussing in this numerical analysis portion. Well, so we start with the consistency. Just to recall, you have already the idea, you know that what is the consistency of a system of linear equation. So if we have a system of linear equation m cross n, n cross 1 and b m cross 1, a general system, just for your knowledge, I have just consider this. So when m is equal to n, we call this as balanced system. When m greater than n, it is called overdetermined system. And when m is less than n, it is underdetermined system. It is nothing like very much related to the syllabus itself, because we will be talking about the balanced system now. But just to give you the overall idea that what are the possibilities and what terminologies are used for each of them. So when system of equations, number of system of equations and number of unknowns are equal, we call balanced system. When system of equations are more than the known, we call overdetermined system. When system of equations are less than n, we call as determined, underdetermined system. Well, so we have a case of unique solution, as you know, when the rank of A is equal to rank of AB, rank of augmented matrix, and that is equal to n. We say we have a unique system of the system, unique solution of the system. And when this rank is not equal to the rank of AB, we say no solution. And when these ranks are equal but less than n, we call infinitely many solutions. This is what we have already learned. And similarly for overdetermined system also the same thing. If the two ranks are equal and equal to the number of unknowns, again you have the unique solution. And when these two ranks are not equal, we have again no solution, and similar, absolutely same. And when two ranks are equal but less than the number of unknowns, we say we have infinitely many solutions. And for the case of underdetermined system, when n is large than m, so we have basically two cases, because this cannot happen. The first one cannot happen. Unique solution cannot happen. Either these two ranks are equal or these are not equal. So when they are equal, so definitely less than n. This is a case where you have infinitely many solutions. And when these two ranks are not equal, you have no solution. So third case, when your number of equations are less than the number of unknowns, only two possibilities are there. The rank of A and rank of AB are equal or not equal. That's all. Yeah. So this is just an overview to start with. So we have a balanced system, overdetermined system, and underdetermined system. And now we will go with the numerical scheme when we have a balanced system, and that too with the unique solution. Those cases only we will consider, because your numerical method will not be able to, give you infinitely many different solutions. It will give you that unique solution. So our problem in consideration will be where we have the solution as a unique solution of the system. Well, so the system of linear equation, Ax is equal to B, A is n cross n, X is n cross 1, and B is n cross 1. So the solution methods. So what are different solution methods? Let me point out here. We have direct methods, so-called direct methods, and we have iterative methods. So there are broadly two categories of methods when we talk about the numerical solution in particular of such a system. The direct methods which you have already seen, that is the Cramer's rule, that is Gauss elimination. We have just seen in linear algebra. We have Gauss-Jordan method, a similar kind of approach like Gauss elimination. We have some kind of decomposition method also, where your matrix A is decomposed as the product of L and some lower triangular matrix and upper triangular matrix, the product. And then you have a possibility of solving X is equal to B. So we are not discussing all those methods, but broadly they are coming under the category of direct methods. I will come to that point, what is direct methods and iterative methods, in a minute. So the iterative methods, the names are like Jacobi method, Gauss-Seidel, very basic. Yeah, this is to start with, iterative methods, but they are very good. I mean, you can definitely use for systems. And there are many other iterative methods also, conjugate gradient, little more advanced than conjugate residual method, and so on. So there are many more methods which fall under this category of iterative methods. Yeah. So here these methods deliver exact solution. That is the difference. First of all, let me just tell you, these direct methods, they deliver exact solution, whereas these iterative methods, they deliver approximate solutions. And here they are very expensive, usually for large systems. So when you have a system with 10,000 equations, these Gauss elimination and Gauss-Jordan and so, they are very, very computationally very expensive. So basically, you cannot think of solving your system using any of these direct methods. And then these iterative methods come into the picture. So they will not give you the exact solution of the system, but they will give you some kind of approximation, of your solution. And they are less expensive, of course. So in iterative methods, the idea is that you will start with some initial guess, initial guess of the solution. And then with your iterations, you will be improving that initial guess, and so on. And after a few iterations, maybe 100 or 200 or 500 iterations, you will get a solution which is quite accurate, not exact, but quite accurate. So this is the idea of these two categories of the method. Yeah, is that clear, this slide? Fine. Okay.
Yes.
Okay, so we go with the some terminology I want to introduce here because we need them for discussing various aspects of those iterative methods. So first is the diagonally dominant matrix. What are the diagonally dominant matrix? So a matrix A is called diagonally dominant by rows. Diagonally dominant by rows if the diagonal entry, AII means the diagonal entry, A11, A22, A33. If that diagonal entry is greater than or equal to the sum of the rest, you are not here adding when j is equal to I, right? So except that you are adding all other entries. So in case of A11, so you have A11 which is bigger than the sum of the rest. Then you call that this matrix is diagonally dominant by rows because you are doing with the rows. You can also define diagonally dominant by columns. If similar thing happen here, but now you are adding the columns. So AJJ, I mean those diagonal entries.
So we are adding the modulus of the columns, like the absolute value.
Absolute values, yeah, in terms of the absolute values. Yeah, in terms of the absolute values. So here, okay, that diagonal entries is bigger than when you are adding all other entries of the column. Then you call that these matrices are diagonally dominant. Yeah, the name itself you don't have to remember much here. Diagonally dominant by columns. So the column entries, when you sum your diagonal entries, is bigger than the sum of the rest in absolute sense. So if the above inequality hold in a strict sense, that means you have only the strict inequality here greater than, then it is called strictly diagonally dominant. by rows or by columns respectively. Yeah. So we have these definitions. Yeah. So strictly diagonally dominant or just diagonally dominant by column, diagonally dominant by rows, or strictly diagonally dominant by columns, or strictly diagonally dominant by rows.
Sir,
So strictly means by all, like all of them have to be dominant in
All.
that
Yeah.
case.
So I 1 to n and j also 1 to n.
so
You know,
like
all
both the
column or
inequalities
all
will have.
rows. Yeah.
Okay.
Again, any question? No question. Okay. I also need to introduce matrix norms because they are also required when we will be discussing about these convergence issues of those iterative methods. So what are those matrix norms? This is nothing. It's just a brief overview. Yeah, we are not going into the details of this because this is again few lectures in linear algebra or matrix algebra. So a number associated with the matrix that is often requires in analysis of matrix based algorithm, and this matrix norm gives some notion of size of the matrix or distance between two matrices. If I give you two matrices, then how will you decide that they are same matrix? So you need at least one number which can define that okay they are close to each other and so on. So that notion of the closeness or the distance between the two matrices, we need such matrix norms. So for example, A is n cross n matrix. Then one norm which is popular, it's a Frobenius norm. Frobenius norms you can compute just by squaring each entry and adding them and take the square root. So this is one kind of norm you can get. So if your entries are of this matrix are really small, some small entries, then this number will be small. So this will tell you how the large entries of your matrix or they are really small, but you are not checking one particular, but you are considering all entries of the matrix. So this is called Frobenius norm. And there is a row sum norm also where you are summing the rows. So you sum each row and then get the maximum out of it. So if you have whatever rows you have, say 3 rows, then you sum each row and out of these 3 numbers you choose one. That is your row sum norm. So all of them have some significance in terms of this matrix distances and all. We will see some applications indeed. That's what we are just defining them. There are column sum norm also which says that the notation is used for A1, here A infinity, here AF. So the column sum is when you add these columns and then pick the maximum one among all these summed values, then that is called the column sum norm. Fine. Okay.
So
So we are
I sir, I didn't understand the maximum thing. What have to like, what we have to take maximum of?
what?
Like what is the thing that we are taking maximum of here? Like we are doing a summation, right?
In this row sum?
Yeah. Can you just
Yeah.
explain by like the drawing the matrix? Yeah.
Yeah, we will come with the example also. So 3, 1, yeah, 5, 2, 1, whatever you have, yeah. You have some matrix. So you are doing row sum. So row sum norm means you sum these. So 3, 2, 5, 1, 6. You sum these 3, 1, 4, and you sum this also. So you have 5, 2, 7, 8. So your norm is 8. Your A infinity norm is 8. Fine.
Okay. Got it. Got it.
Yeah. So you are
Sir, can
summing
you
all
say one
rows.
thing about
Eh?
sir Frobenius norm? Can you say
Frobenius
once again?
is much easier. You square each entries and sum. So you have 1 square, you have 2 square, you have 3 square, you have 0 square, you have 3 square, you have 1 square, you have 5 square, you have 2 square, you have 1 square and square root. Clear? So you
Yes,
have,
sir.
there, and not only these three norms, there are many norms. So there is a general definition also of the norm, that when we call norm, so there are not only these three norms, there are hundreds of norms we can define. So anyway, we are not going, as I said, much into the details of this. We need some idea of the norms. So I have just given you that there are some kind of numbers associated with a matrix, which tells you in some sense about, how, large entries such matrix has. Those things
Excuse me,
are
sir.
there. Yeah.
Sir, in row sum norm you return subscript infinity, and in column sum norm you return subscript 1y.
Yeah, there is no reason as such for this. It's a notation which is very standard and used in all sort of literature. The reason has come from the vector norm. Basically, when the first definition comes for the vector norm. So when you have a vector, this is generalization of that. For example, you have this vector. Here also we define the norm, means what is the length of this vector. So that was like x, the two norm. If you define, this is 1 square, 2 square, 3 square, right? This is the also a vector norm. Similarly, the one norm is there where you get the maximum, not maximum. The one norm is you just sum all entries 1, 2, 3 in our case one. So or I will just write down 1 plus 2 plus 3, right? This is x1 norm. So the vector 1 norm with absolute value, of course, in this case all are positive. So this is 1 norm. And there it was infinity norm, which was slightly different because all these norms were coming into one category, which was p norm. So xp was defined as summation xi power p and then 1 over p. In general, the definition of pth norm was this, where this 1 norm, 2 norm, 3 norm, 4 norm all comes under this p norm. Then in this continuation, there was a definition of the infinity norm also for vector norm. And that was the maximum you take of all these elements of that vector. So maximum over I and xi. That was actually defined for vectors. That maximum norm was denoted by infinity. And there is some correspondence between that infinity norm and this row sum norm, and this one norm and this one norm. So there is some correspondence which is well established result in matrix algebra. So from there, the notations have been picked. So this is basically earlier it was defined for vectors. Yeah, I can give a separate lecture on maybe 1 hour, 2 hours on these norms itself. So to just to brief if time permits, but unfortunately we don't have much time. And in any case, whenever we have time also here in we don't go to that details explaining so many things about, because there's so many properties which relates from this matrix norm to the norm of vectors, and then vector norms itself have so many properties. So there is a lot to be discussed in many lectures, not in few lectures, of course. So but you don't need that here for numerical
And
analysis.
sir, hello sir.
Yeah.
And sir, you enclosed the a by 2 modulus sign. What is the meaning of that?
A by 2.
No sir, 2 modulus sign.
Where?
Sir, a. Sir, you
A.
enclosed. Yes sir, and 2 modulus sign. That is,
Oh,
sir,
this
a
one.
vertical line.
Oh, this
No
is
sir.
for norm. This is the notation for norm. Yeah, yeah. Oh, I forgot. This is the notation. So in vector, in matrices, the standard notation for the norm is this. So whatever norm you are computing of X or matrix A, the notation is this one for the norm. Like for absolute value, the notation is this. But absolute value you use when you have only one real number, right? You have one real number,
Yes, sir.
minus 3, then that is the absolute value of this minus 3 is just 3. So it actually begin from there itself. But when you have one entry, this is fine. You are checking that absolute value and measuring that how big is that number, right? How close
Yes,
it
sir.
is to zero. When you have a real number only, this is the zero here, and then by absolute value, you are judging that how close it is to zero. Similar concept was extended when you have two entries there, you have a vector of two components. Then how to judge the largeness, the size of this vector. And then the idea has come that, okay, this is also a size when you have 2 square, 3 square. So this is also kind of a size which is related, this number is related to this vector. Or there are many other, taking just the maximum out of this, that 3, because that is the largest one among all these. So the 3 is also a number associated with this matrix, which gives some information about that vector. Sorry. So that idea got generalized for matrices also, because we need for matrices also that what is that size of that matrix somehow. So these are some indicators. Yeah, these are just the indicators. There is no unique, a very general definition. A very general definition is there for norms, and under these three, for instance, here they fall into that category. So there are some nice properties of the norms we are missing here in this lecture. Yeah. So, but main topic is not about the norms and all in this numerical analysis. Yeah, where we are discussing how to solve a system of linear equations using iterative methods. That is the topic. So let's go to iterative methods. So here the two topics I have just very roughly introduced you. One is the diagonally dominant matrices, and the other one that the iterative method. Now I'm coming to the iterative method. A method for solving linear system is called iterative. If it is a numerical method means you will be getting some kind of approximations, right? Some numerical values you will be getting, not the exact answer, right? So a method for solving the system is called iterative. If it is a numerical method, computing a sequence of approximate solutions that converge to the exact solution x as the number of iterations k goes to infinity. What do you mean by convergence? So again, the roughly you just understand that when this we will start with x0, the initial guess. So if it's a 3 by 3 system, we will take some initial guess. Let's say 0, 0 we started with. Then by some, the scheme, we will compute the first values after first iteration. So they will of course be changed. You will get some other value and so on. And you will be computing that. So this is your second approximation, then you have third approximation, then you have fourth approximation, and so on. And then you have this,
So
keep
the
on going.
superscript here just means that we are actually making it go towards more accuracy, just that only.
Yeah, as we are moving further, we are supposed to have a better and a better and a better solution. Yeah, of course. Yes. Then if our scheme is good, then definitely that should happen. That if you go for more iterations, you should have a better result, better approximation to the solution. And what do we call that? Converge, that this scheme will converge. When you keep on doing that, and theoretically we say that this number of iterations goes to infinity. Yeah, that will not happen in a finite time. In general, maybe by chance sometimes this may happen that it just fall in the iteration to the exact solution, but that hardly happens. So in that case we are not considering. So usually what happens here, that when n goes to infinity, the number of iterations goes to infinity, then the sequence goes to x, the actual solution. That should be the tendency of that numerical method or numerical scheme. Is that okay? We are following something?
So means we are actually running things in a like a
Give
loop.
some.
Yeah. Yes, sir, can you give an example?
Yeah, Tanmay, you speak first. What did you say?
So I was also like saying to give examples more to understand,
To be?
better.
You got some idea?
Yes, but with an
Yeah, we will
actual
be doing many examples and so on. This is just the beginning. So don't worry about this. You will get, of course. But here, just my point is that we use that always whenever there is a scheme, there is iterative schemes, in particular iterative schemes, we always use that word converge, because your iterations are moving from some initial guess to the next. So naturally, you will not go for infinitely many terms. You will be taking some finite terms. And then you say, okay, this is my approximation. But the nature of that scheme should be, or mathematically we should be able to check whether when we go and approaches to infinity, when we go towards infinity with these iterations, whether this scheme will take you to that actual solution or not. So, because then only that scheme is reliable, right? Then only you can expect that large number of iterations will give a better solution, because you know that when a number of iterations goes to infinity, will be getting exact solution. In practice, you will not be going for infinity. Yeah, there is nowhere infinity. So you cannot get to that. So you will be already having 1,000 iterations or 2,000 iterations or whatever. And then you will stop that. But the method should be of that, the characteristic of the method should be that it should converge theoretically when k goes to infinity. Yeah. Is that fine? We move with that. So the idea of deriving, how to derive an iterative method, that is what we will learn now, that how to derive such a method, and that to such a method which will converge. So you consider a system of linear equation, and the idea behind all iterative methods, we will be learning some of them and some of them we will not be learning, but it is based on kind of splitting of A, that you split A. So just a general idea, it's not a particular method. We will go with the particular method in a minute. The general idea is that you split A, let's say P matrix and N matrix. Yeah, just minus sign is taken for simplicity. But you have A, you have split it into two matrix. Yeah, some P and some N. Well, once you have split it in such a way that P is a non-singular matrix, then given system Ax is equal to B is now P minus Nx is equal to B, or you have here Px is equal to Nx plus B. Yeah, Px is equal to Nx plus B. This is our system now. The same system, just splitting that matrix A, we got that Px is equal to Nx plus B. So we have this relation here, Px is equal to Nx plus B, and now we consider the iterations with a suitable guess, x naught. The idea of the splitting is that both the sides you have this x. In fact, now P is invertible. I should mention here itself. You go with the multiply by P inverse. So what you are getting here, x is equal to P inverse N x plus P. So you got left hand side x, and you have naturally right hand side also x with some these matrix multiplication here. So,
So there
Hello,
will be
sir.
P inverse B, no?
P inverse B, sir.
Yes, sir. P
P
inverse B
inverse
should
B,
be
yeah,
there.
yes, P inverse B, right? So we have started with the x is equal to B, and somehow we have splitted that A in such a way that we are getting x is equal to something here of x plus something here h, right? B, something, some such splitting we got out of our system. It was Ax is equal to B, and we want to have a splitting such that we have left hand side x and something on right hand side x and something constant. Fine. And then once it is there, the idea is that you right hand side you plug some initial guess. You plug some initial guess. See, remember, this equation x is equal to gx plus hb will be satisfied for actual x, the exact solution x, right? this splitting, because x solves this Ax is equal to b. That means x satisfies this also, x is equal to gx plus hb. So what we do, we start with some x0, some initial guess. We compute this gx plus hb, we get a new x now. Correct? Now this x you substitute there, you get a new x. Then you substitute there, you get a new x. And you keep on doing that until you feel that now, okay, things are not changing. You are getting almost x is equal to this, let's say you have n minus 1th iteration, you have nth iteration. If this nth iteration and n minus 1th iteration, those values are close, so that means you are getting a good enough solution. This is roughly you will get that idea, because ultimately your exact solution will satisfy absolutely that x is equal to gx plus hb. If that equality happens with some x, that is the actual solution. But we have started with x0, got x1, then again x1, we got x2, then x2, and we got x3, and so on. By doing
So
this,
the initial value x0 we are taking by a suitable guess, but
yeah.
based on, like, we have to keep certain things in mind, right? Like, before taking the guess, like this should be fulfilled and on. So what should be those conditions that should be fulfilled? Like,
It is not very, that you, because you don't know the solution, right? You don't know the solution. So you don't know exactly, maybe your solution is 1000 and 500 and the third component is 600, but you don't know what is the solution, right? So you will start something 0, 0, 0 or 1, 1, 1 or something. You have to start it. Automatically, this will take care after a few iterations. It will take you to the solution. It will take you towards the solution. That is the idea of developing those iterative methods. So
we
it is
can
not very
select
much.
anything as anything as x0, and it will automatically take us to the actual solution as after a particular number of iterations.
Yeah. So in principle, a scheme is called convergent. A scheme is called convergent if for any initial guess you take, and the scheme will take you to the actual solution after, when n goes to infinity. That is the idea of the iterative scheme, the convergent scheme. If it is not convergent, then anything can happen. You will start with some whatever guess you take, and then after sometimes you will see something, nonsense there is happening. So some unrealistic values will be coming.
So how
Yes?
can we make suitable guess?
How can
we make suitable guess?
That's what I said. That in general there is no algorithm which can take you, okay, you take this guess only. So you start with some guess, but suitable means if you know the problem already, right? You know the problem, you might have modeled some physical system, and then you got that system of equations, and you have some idea maybe of the solution, the nature of the solution, that it is going to be large, entries, positive entries or negative entries or whatever. So if you can guess from that physical system is fine. But once, as I said, we have an iterative scheme, we have a convergent scheme. It is not dependent on initial guess. You take whatever you want. It will maybe few more iterations. That's all. It will take few more iterations, but there is no problem. Yeah, maybe 5, 6, 10 more iterations. If you have a better guess to start with, it may take less time. If you have started with a bad guess, in the sense that it is far from the solution, there is no relation with the solution, so then it will take little more time. But a convergent scheme will get you the solution.
Sir, a scheme will be like this convergence of the scheme will depend on how we split the matrix, right? The P and N.
Absolutely, because different splitting will give you a different scheme, first of all.
Yeah.
Yeah, different splitting will give you a different scheme. Some scheme we will mention that if you do that splitting in such a way, we are getting that Jacobi method, well-known Jacobi method. Why they are well-known? Because that splitting is working for many cases. Yeah, that is splitting is convergent for many problems. That's what these, and otherwise you can have your own splitting. It's not like Jacobian Gauss-Seidel has given the scheme. You can have also your splitting and you will get something. But then you have to check that which one is better, whether the Jacobi Gauss-Seidel is better or your own. And then you will realize, and if you don't realize, then you will get a method. Otherwise, you will realize that no, okay, Gauss-Jacobi and Gauss-Seidels are better because of these reasons.
So how do we judge if a scheme is better? Because anyway, in any scheme, the exact solution will be found only after infinite iterations.
Yeah,
So,
that is called the speed of convergence. There is another term, speed of convergence. So, for example, you and your friend, they start running at some point, yeah? At the same point. Then one of them will win. Who will win? Who will run fast? You both will reach to the destination. That is fine. But one will run fast and that person will reach fast there. Yeah.
yeah.
So similar thing happens here also, that both the schemes are convergent, for example. So whatever initial guess you say, both will take you to the exact solution, but there is a speed. One is faster, one is not faster. So that faster one is good, because after only few iterations you will get your good solution, you will get a very good solution. But in a,
So how can we select the faster one from the initial? Like we
how to
won't
check
have
the
any idea,
faster?
right?
Yeah, that's what I am teaching here. Yeah. So we will learn. This is what mathematics
Sir,
is
some guess
beautiful. Yeah,
can
it plays
diverge
important
also.
role. Yeah.
Sir,
Sometimes
some
you
guesses will diverge also.
sometimes you don't take interest when we teach something abstract, like linear algebra. Maybe to some of you was very abstract. Oh, what are we talking about? This vector space, eigenvalues, eigenvectors, and so on. What is these things? Yeah, we have this feeling. We used to also have, and probably more even, because our teachers were not, in fact, very much relating to the real life problems. Now the trend has changed, and we are more into it. We always try to relate to the reality. So this is the point now. So we have just learned eigenvalues and eigenvectors. What you will realize here, that those eigenvalues and eigenvectors, in particular in this case eigenvalues, will tell you the speed. Did you get my point? So those eigenvalues, which we had a very theoretical, perspective, that, oh, what are these, ax is equal to lambda x, and you are getting some numbers, something. Though we have already seen some applications of that. But now here you will see beautiful applications which can tell you the speed of such a scheme, that whether it will be fast or it will not be fast, whether it will converge or it will not be convergent, whether it will converge or it will not converge. Those numbers can tell you that even. Yeah. So those results, those very fundamental, basic mathematical results, all they are used in somewhere. We have to just wait and watch. But all whatever abstract things, whenever you feel that, oh, what is the use of it? Maybe you don't see use because it's not suitable. Now, if I explain you something which is not relevant, the system of equations is relevant. I can relate you with how eigenvalues are used here. But there might be some topics which I cannot relate at that point itself. Yeah. So like two variable differentiability, we have discussed a lot and so on, but we don't have direct examples where we can, show you that what is the importance, why we are studying this. So everything we don't relate, but there are a few things where we can actually see that there, and for other you have to wait a bit. Yeah. So well, so is that okay? So I think you got a very good idea about this with this discussion. I can realize that you have a splitting. The splitting, what you are doing kind of, as I mentioned before, you are trying to get something. Sorry. You are trying to get such a relation like gx plus some hb. Yeah, such kind of equation you are trying to derive. so that you pass the initial guess to the right, you get a new, and then you pass it here, then you will get there, then you get it, give it to this, and then it will give you back. So some kind of iterations we can set up like this one. Yeah, I mentioned here. So out of this you can skip. I mean, I will introduce this x case once I multiply that P inverse. So here you have, out of this, you are getting x power k plus 1. So k plus 1 is denoting the k plus 1th iterations. Yeah, after k plus 1th iteration. The right hand side, the G is nothing but P inverse n. G is P inverse n, just a new name for this matrix I have given G. Plus this HB, the H is nothing but P inverse, nothing else. So you will get out of your AX is equal to B after some splitting and then introducing this iterations. So we get our iterative method. This is our iterative method. Can you guess here what is most important in this iterative method? What could actually, be crucial for the convergence we were talking about, for the speed we were talking about? Which because see, the B is given, X we want to get. So what is important here? This H and B. So in your opinion, which is actually more crucial for a iterative method? Should be. I mean, can you?
I think G.
You think G?
G,
Yeah.
sir.
Yeah.
Yes.
All are
Yeah.
thinking G. I think. Correct.
Yeah, it seems so, because every step it is multiplied with the previous steps.
With the previous one. So this G is, very good explanation. So this is precisely also the reason which you will see now in a minute, that G is actually important. The H is not so important. You have H, B, a constant factor sitting here. Yeah. H is a constant and B is also a constant. In the beginning it is given. So this is something ideal. But GXK, this is multiplying the previous solution. So this is actually very, very important, the G. So this G is called the iteration matrix. Yeah, G is called the iteration matrix. H has no name. So the G is important. The G is called iteration matrix. Well, so I think now I can introduce, because we have a method. I mean, see, this is not some particular method. It's a general setup of an iterative method. So with this, I can introduce again a little more formal definition of the convergence of the iterative method. So iterative method is said to converge for any initial choice, for any choice of initial vector x naught is equal to r power n. The sequence of approximate solutions xk converges to the exact solution x. Yeah, an iterative method is said to converge if any choice of initial vector x, the sequence of approximate solutions converge to the exact solution x. That is how we define, how we call that a method is convergent. Yeah, a method is said to converge for any initial choice if the sequence this xk converge to the exact solution. This is what we have discussed also before. The error, how to measure that error in our iterations, how much the error is. So we call that vector r, which we are defining here, r, with b minus axk. See, your solution, your system of equation is ax is equal to b. So b minus ax, if x is exact. What is b minus ax if x is exact?
So it will be 0.
0.
It is a 0 vector. B minus ax will be a 0 vector when x is exact. But in our sequence here, we are not getting exact. But you can realize that if b minus ax is small, it's close to 0, 0, 0, 0 something, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 2, right? Then you can think of that, okay, yes, our solution is good enough now. So if b minus ax, this vector, is a small vector. Again, that is smallness, how to check that smallness, the size of that I discussed already, that we have for that purpose those norms which we call. So if these vectors having very small entries, then we can think of that, okay, our solution is good enough now, because the actual solution, this kind of residual, we are talking about this residual. So this residual is actually 0 when we have the actual solution here placed. But now we put the approximate solution, and this is a very small vector. Then we call it that, okay, we can stop it. So this is used very much for stopping your iterations, because you don't know the actual error. The actual error is here, x power k minus x. But do you know x? You don't know x, right? You don't know x. So you cannot get xk minus x. So you cannot get the actual error.
Sir, if we calculate like xk plus 1 minus xk, and if it is getting smaller, the norm is decreasing. So can we say the A is convergent? Like
yeah, if you compute xk plus 1 and
minus xk,
and you
like
compare with xk, right?
yeah, basically like we consider the difference of those matrices of the ith and I plus 1th steps, and if we see that the norm is decreasing, we can say that the like the method is converging, right?
Yeah, we'll come to, we are getting into the similar kind of directions, which we will just come in the we'll discuss on the next slide. Yeah, but you are right. Yeah, so something of that nature. But this residual also gives you that indicator. See, one indicator is that xk plus 1 and xk, they are close to each other. If they are close to each other, means you are not getting any improvement in your values. So that means kind of convergence has come. So you can think of that this is the good solution. Or you check this b minus ax, because this is everything is available, a is available, b is available, x is available, and you check this one, this residual, and residual will also give you that indicator, will give you that indication that you are actually, now you can stop your solutions and say this is my approximate solution. Clear?
Yes, sir. Yes.
Excuse me, sir.
That point? Yeah. So in general, we have no knowledge about EK. EK is the error because we don't know X. So how can we get EK? Because the exact solution is unknown. However, it is easy to compute RK. So the convergence is dedicated on the residual in practice. So in when you solve the problem, we usually check that how large is this RK. Once this RK is small, you can stop it and say this is our solution. There are things are not so straight also. I mean, though I will not go again to that much detail into the numerical analysis, but these residual part, there are problems. There are some problems AX is equal to B for some special matrix, and they very often happen in practice for practical problems, that this RK is very small, is close to 0 vector. Yeah, RK is close to 0 vector, but that X is a very bad approximation. Very bad in the sense it is nowhere close to your solution. Your solution was, let's say, 111, and your X is coming large number, 200, 500, and 900, and your residual for this large number is also close to 0.
So how can it happen?
Yeah, that's what. So
then how can we rely on this definition?
yes, so we cannot actually rely very much on this. That is also true. For that reliability also, we have a mathematical tool which is called, one number is there. That number is called condition number. So we need to get the condition number of our problem, of our Ax is equal to B. So we have to find the condition number of this matrix. And that condition number of this matrix will tell you if that condition number is close to 1. It's a small number like 1 to 10, 20, whatever. If it is a small number, that condition number of A, then this residual will give you, the actual meaning, it will not mislead you. But if that condition number is very large, if condition number is 5,000, if condition number is 1,000, a large number, in that case, there is a chance and very high chance that the solution which you have stopped based on your residual, that may not be the solution at all. And those problems are called, there is a name for those problems, ill-conditioned problem. Yeah, when the condition number is very large, those problems are called ill-conditioned problem. And for solving those ill-conditioned problem, it's a challenging task where you need some kind of special iterative methods. They need special attention, and with usual methods, you cannot solve actually those problems when the condition number is high, the condition number is very large. So there are so many details, very, very interesting details which are there, which definitely we cannot cover here. But it is fine. I mean, you need not to go through everything now in the first year, this very general course. For that, you have to learn numerical analysis, right? A semester course on numerical analysis. Then you can get all those ideas. So here we will consider all those systems who behave well, a well-conditioned system we call well-conditioned system. So we'll be working with well-conditioned systems, and those well-conditioned systems you can rely actually on RK. Is it okay? Yeah. So we move, I think, because it is actually, it does not make sense to go into that details now in this course. So, but this is, those problems are special, as I said, where the condition number is very large. Those problems are very special problems. So in general, you have a well-conditioned matrix. So your condition number is like 3, 4, 6, like that. And there are no problem. This are, and there is a nice theory. It's not just, I'm just telling you. There is a nice theory which
Hello,
you
sir.
can see that why this is happening. Yeah.
Sir, what is condition number, sir? I didn't understand.
You can leave it actually, I would say. Yeah. So the condition number, I mean, if I can give you, so I can give you some idea. So it is like norm of A and multiplied by norm of A inverse. That is how the condition number is defined. And this number, norm of A and norm of A inverse, that actually gives you a lot of information. That's what a new name for this product has come as condition number. So this condition number tells about the condition of the system. Yeah, whether it is a well conditioned or it is a bad condition. Yeah, ill conditioned. The term is used as ill conditioned. So those ill conditioned matrices are really, really tough to solve, first of all, using these iterative methods, because when you use any method in computer, there is a truncation, yeah, in the machine, because you are not getting all decimal places, you are truncating somewhere, and that error itself for those ill-conditioned system, that much error can lead to something very, something very different answer, which is not at all related to the actual answer of the problem. But those things happened with these ill-conditioned matrix, ill-conditioned systems, not for well-conditioned system. Well-conditioned, everything is nice. So we don't go into that much details now. I'm just making you afraid, probably. So everything is nice. Yeah, forget this discussion. We have a residual which can tell you about that how this method, or whether you are in a stage to stop that iterations, or you have to continue the iterations depending on how large or how small is your RK and what is your desired accuracy when you have to stop. So depending on those, this plays very important role, this residual actually. Okay, shall we go with the Jacobi iteration method at least in next 5 minutes? I think 5 minutes will be over with the Jacobi method. So for the Jacobi iteration method, you consider a system AX is equal to B, and then in splitting you have to do first write that L, D, and U. L is the lower triangular matrix, D is the diagonal entries, and U is the upper triangular matrix, right? So when you have A here, this portion is U, keeping all other zeros, and D keeping all other zeros, and L here keeping all other zeros, that is your L. So you have L plus D plus U. When you add 3, you are getting A, right? You are getting A. So A is nothing but this lower triangular matrix, the diagonal entries, the upper part. You have L, D, and U. Okay?
Yes, sir.
Yeah.
Sir?
So
Hello, sir.
yes.
Sir, there we took two like splitting P and minus N.
It's
and
okay.
here
I can do that easily. So L plus U
yeah,
I will make 1. There was what was name was there was
P
something
and minus N
P and
minus N
P minus A.
N.
Yeah, so that is fine. I mean,
Yeah.
2 or 3, that is not important. Important is splitting. So A is LDU. So your AX is equal to B is L plus D plus U, X is equal to B. And as per the Jacobi method, we are keeping this D term X here and pushing the other one LD to the right hand side. And assume that D inverse exists, then only this makes sense. So this D inverse exists. And then we have here this scheme X is equal to D inverse L plus U plus D inverse X. And introducing these iterations now, the Jacobi iteration method is here. Xk plus 1 is equal to minus D inverse L plus U, Xk, and D inverse B. And this okay, in component form. Yeah, so this is okay. This is your iteration matrix. Yeah, this is your iteration matrix. Because iteration matrix is very important. We have to analyze iteration matrix for its convergence, for speed of convergence, so many things. So that G is very important. This G is very important. But this matrix vector representation you can also write in component form. Component means you have here x1, x2, x3, right? You have here also x1, x2, x3. There are n components. So that in component form you
Sir,
can.
so hello. Yes, sir. So basically, if D has at least like in the diagonal matrix, if at least one diagonal element is 0, then we say that this method is not applicable because
Yeah,
D inverse doesn't exist in that.
yeah, exactly. If the diagonal entries are 0, any of them, then D inverse will not exist, right? Because D
Yes,
inverse
sir.
is nothing but the inverse of the diagonal entries, correct?
Yes, sir.
Yes.
Yes.
Yeah. So in component form, this D inverse here and D inverse here also will give you this 1 over A11 term. Yeah, let's start with this first. So you have, because of D inverse, you have here 1 over A11, and then because of this B, you have BI term. We are talking about ith component, then minus here, then minus here, and then again D inverse. For the D inverse, it is 1 over AII sitting already there. L plus U. L plus U means you have left the diagonal entries, right? And you are multiplying with this X. So it is like AX only, but leaving that diagonal entries. So that's for this summation has come J1 to N, but J is not equal to I because diagonal terms are not there in the A. And you have Aij and Xj power k. So this is in component form if you want to write this. Otherwise, this is a matrix vector form. Is it okay? Did you get the idea?
Yes, sir.
Very well.
Yes,
So you
sir.
go through this, again, and tomorrow we will start with the Gauss-Seidel one. So this is, I think, good point to stop here itself. So we have at least introduced that Jacobi method. Yeah, in the next lecture next week we will start with the Gauss-Seidel and do some examples, some iterations, and then all details. Then we will go for the convergence, the speed of kind of things, how fast and so on. So in 3 lectures we will finish that. Yeah, so we need 2 more lectures, that's all. In 2 more lectures we can finish this. So next week the iterations will be over and we will start in fact with the topic. So good. I think you go through again those slides, and if you have any question, you can get back to me. It's okay. So we can leave now. Yeah, you can leave for.
Sir, can you explain the component form once again?
Yeah, the component form. See, if you have this D inverse, so what is D inverse? D inverse is 1 over A11, 1 over A22, 1 over ANN. Correct?
Yeah.
This is your D. What is your B? I'm explaining this term, and then you try it yourself. Huh? B is B1, B2, Bn. So when you multiply, what will happen? B1 divided by A11. Second term will be B2 divided by A22, and so on. Bn divided by Ann.
Yeah.
Clear?
Yes,
So
yes,
this is here ith term I have taken. So therefore Bi over Aii. Similarly, out of this you can make out that this will come. Yeah, please.
So you haven't uploaded the slides of previous lecture. Can you do?
I think I have done it yesterday night. So I was a bit occupied yesterday. There was some issues I could not do immediately. Yeah. Good.
Okay.
So well.
Thank you, sir.
Have a good day. Stay safe. Take care.
Excuse me, sir.
Sir.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.
Excuse me, sir. Sir. Hello, sir.
Yeah, you want to say something?
Sir, for quiz 7, how to find the eigenvalues for that question?
I have introduced that idea yesterday. You were present in yesterday's class?
Yes, sir.
There was.
Sir, actually the problem is that when we do row reduction there, we get the
Don't do
final
row
reduced
reduction.
matrix.
Come on, guys. There was. The sum was same na for all.
Yes, sir. Yes, sir.
The
From
column
the
sum.
sum we can get. Yes, sir.
You approach in that way. I don't think you need to get anything out of that. With that itself, you will. Yeah, just think about and let me know if you did not get it. Yesterday example I have done with that you have the rows sum equal to 1, then what will be the one eigenvalue. So one eigenvalue we got. That is a very good question actually. You should understand that, which I have given today in that quiz. That is a very good question, and I am sure that you will find the answer. Yeah. There was something characteristic. What did I ask there? I forgot actually, but it was a nice question.
Sir, you asked about the eigenvalues, the algebraic and the geometric multiplicity and all.
Yes. So you have to use probably several properties that sum of eigenvalues is given, product of eigenvalues is given to you, and one eigenvalue is given to you. Geometric multiplicity is given to you. Corresponding to that eigenvalue you can find easily. So you have to use so many concepts there. I have given you the hint.
Yes, sir. From that we are getting 15
one
and the
eigenvalue you
zeros.
will get. One eigenvalue you will get easily.
Yes, sir.
And corresponding to that eigenvalue you will get the eigenvector.
Yes, sir.
And with that eigenvector you will get the geometric multiplicity.
Yes, sir.
So the geometric multiplicity, then algebraic multiplicity will be more or equal to that. So you will get geometric multiplicity of that number also. And that
Yes,
the product is known to you of the eigenvalues, and you will get the other eigenvalue also. I think I have given you enough hint.
The product of eigenvalue is the determinant of the matrix.
Okay, yeah, sum. You use sum, then sum of the eigenvalue.
we have to use both the product as well
I
as
think product
the
don't
sum
have to use
to get
probably. Product is not required. I think the sum is enough. The sum of eigenvalues.
Sir, can you release the results of the two
Yeah,
assignments? I cannot see the results.
I will release. I did not release it. Huh?
Okay, sir.
Fine.
Thank you.
Good. Okay. Take care.
Sir, actually, by using the properties that you taught in yesterday's class, we are getting the answers as 15 and 0 and all those answers. But the problem is that when we do row reduction, we are getting different eigenvalues. We are getting 4 zeros and a 1.
Full? Don't do that. It is much simpler. It is much simpler. You get one eigenvalue, you get the corresponding eigenvectors, and corresponding eigenvectors will hint you that how many distinct eigenvalues are there. If I remember correctly,
Yes,
there are two distinct eigenvalues only. One which you will get directly, and there is a one more. So the one which you get directly, its algebraic multiplicity also you will get, because that will be equal to the algebraic multiplicity, because it cannot be greater than that. You will realize in that problem. So it will be equal to that, and it has to be equal to that you will see. And then the other one you can find out. So you found all eigenvalues, eigenvectors, everything. Yeah. Just think again and discuss. If you don't get, discuss with me.
Sir, if we found one eigenvalue,
Yeah.
then how to get the eigenvector? Means we have to solve the determinant. To put it in
क्या
the matrix.
प्रॉब्लम था यार, तुम सॉल्व कराओगे क्या मुझसे? यहाँ क्या थी वो प्रॉब्लम?
1 2 3 4 5.
1 2 3 4 5 है?
Horizontal.
Oh, horizontal. 1 2 3 4 5. 1 2 3 4 5 and so on. So A 1 1 1 will be what? 3 3 6 15 na? 15 1 1 1, right? Is this the relation? So I know one eigenvalue.
Yes, sir.
Is 15. Is that okay?
Yes, sir.
So one eigenvalue is 15. And what is the idea now? What is the sum of all eigenvalues? What is the sum of all eigenvalues?
15.
Also 15. So
Yes.
what is the other eigenvalue? See, sum is 15 and one of itself is 15.
0.
0. Why 0 is the eigenvalue? You can realize also from the matrix itself. The determinant is 0, right?
Yes, sir. That's why I told that we can use product also.
Correct.
So we will get 0.
So the determinant is 0. So that means 0 is an eigenvalue. 15 is an eigenvalue. What is the geometric, what is the eigenvector corresponding to 0? One, two, three, four, five. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. Right? X equal to 0.
Yes, sir.
From here, when you reduce, what you will get? 1 2 3 4 5 0 0 0 0 0 0 0 and so on, right?
Yes, sir.
How many free variables?
4.
4. So what is the geometric multiplicity?
4.
4. So algebraic will be how much? 4 or 5? Algebraic is always more, huh? You know that.
More or equal.
So more or equal. So algebraic will be 4 or 5. It cannot be 5 because
Yes,
1 is
sir.
already sitting there. So it has to be 4.
Yes, sir. Yes.
So the algebraic
Yes, sir.
multiplicity of 0 is 4. That means 0, 0, 0, 0 and 15. These are the structure of all eigenvalues. I think that problem is solved now.
Thank you, sir.
Yeah?
Yes, sir. Yes, sir. Got it. Thank you, sir.
Okay.